There we go. Okay. It's recording now, and we can go ahead and get started. So we're just going to work through a handful of the review problems. I've set aside several of them to work through today. And we're going to start off. I'm just going to go down the line in order. And if at any point anyone has any questions, feel free to say something in the chat or over microphone. So we'll start off with problem 1. Figured this is a good starting point. So problem 1 in the dynamics review. So I'm going to go ahead and draw out this diagram. One last confirmation that the video is being picked up. Is there any kind of glare here? Not really. Cool. And I need an eraser. Okay, so problem 1. We have a structure that kind of looks like this. With this being fixed. And we have our point here, A, that has an arm that goes out to there with a connection at B that goes out to C. And has some kind of hanging thing here. We are given that AB has a constant clockwise angular velocity of 0.8 radians per second. So it being constant means that our alpha AB is 0. So anytime we have constant angular velocity, our angular acceleration is going to be 0. We also know that BC has constant clockwise angular velocity of 0.2 radians per second. So omega BC is going to be 0.2 RPS, radians per second, and alpha BC is also 0, just like AB. We are asked to find the acceleration of part D. So we're looking for acceleration at D. So we can go ahead and classify motion. We're going to know that AB is a raphistic, BC is going to be a general planar motion, and then D is going to be translation moving straight down. And something else worth noting is that acceleration here at D is going to be the same as acceleration here at C, because this piece of the structure is stated to be locked vertically and never move from this position. So as C moves around, this is going to follow it and move in the exact same acceleration as the end of C. So we can go ahead and start writing our acceleration equations. So starting with the point here in the center, we can say that acceleration B is going to be equal to acceleration A plus acceleration of B relative to A, which is equal to acceleration C plus acceleration B relative to C. Using that equation, we can draw our kinematic diagrams. So we know that point A here, we're treating A, B as a raffle stick. So this is going to be a fixed point. So we're going to have something like this, with this side being A. Sorry, that should be for the B relative to A. Where this is A and our end here is B. B is going to have the acceleration tangential and normal. So AT and AN. I just want to see how this looks. That looks pretty good. So coming back to our acceleration at A, we're treating A as a fixed point because it is. This is a stiff piece that doesn't move, and so A also doesn't move. A is going to be just a fixed point constant. Where this is A. That's going to be equal to AC, which AC can be modeled as unknown acceleration because it's going to be moving on the end of a general planar motion. So what we can do is we can represent this as ACY and ACX. So all this is stating is a Y component and an X component for the unknown acceleration AC. We can then move over to B relative to C, where we treat C as a fixed point. So we're going to say plus where this side is C, this side is B. And there is an AT and an AN. From our information that we'd found at the beginning, we can say we know that AT is alpha R. And AN is omega squared R. So using these two rules, knowing that the alpha values for both pieces are 0, we can go ahead and say that AT here is 0 and AT here is 0. Then our AN values, omega squared times R, we have 0.8 times the radius. I think we were given the dimensions. Yes, we were. This being 300, what is it, millimeters? Yes. This one being also 300. So that's where we get our radius value from. And we can say AN for B relative to A is going to be equal to 192. And that is in millimeters per second squared. And then AN for B relative to C is going to be 0.2 squared times 300 millimeters. So AN over here is yeah, that seems right. 12 millimeters per second squared. And so we found our acceleration components. A is stationary, so this is essentially 0. And we have our two unknown pieces here. So we can go ahead and, after establishing, because we are given the last thing we need, that this angle here, that angle is 50 degrees. And this angle here, that angle is 15 degrees. I'm writing it over here, even though it's given in the problem as being on top, because the angle here and here would be the same. This angle and that angle would be the same. And that's the way they write it. They show 50 degrees and 15 degrees. Okay, now moving on, we can, I just want to make sure the camera can see all the way down to like here. Okay, I'm gonna mark this. So we would do some of the forces on Y, some of the forces on X. Some of the forces in X is going to be equal to 0 plus, we say, well, we'll say minus because our AT value is 0 and our AN value is going down and to the left. So we'll say minus cosine of 50 degrees. Cosine of 50 would give you the horizontal piece. So we'll say the 192. Oops. Equal to ACX. We'll say plus because AN here is going down into the right. So plus this way, cosine of 15 would give us the horizontal component. So this is going to be 12 cosine 15. And then you can solve this and you end up being able to say that ACX is equal to minus 135 millimeters per second squared. So that's the X component, and then we still need the Y component. So we'll say some of the forces Y equal to 0 for this piece again. And we'll say minus because AN is going down. So minus 192 times sine of 50. That's equal to ACY. Minus AN is going down, sine of 15. And you can say that ACY, after solving this, would be equal to minus 144 millimeters per second squared. So then finding the overall magnitude of the acceleration, AC is going to be equal to the square root of the sum of the squares of its components. So that's going to be minus 135 squared plus minus 144 squared. And that value would come out to be 197.4 millimeters per second squared. The last thing we'll need for this is an angle. And if we know that our components, if we start from here, our x component goes left and our y component goes down, we know that because we have minus and minus. So our acceleration is going to look something like this, drawn from the start point to the end point. So we can find this angle by doing tangent of this theta. And I'll just write this here. So tangent of a theta, right, of this theta can be equal to opposite over adjacent, opposite being the y, adjacent being the x. And we can solve for that angle just by doing inverse tangent of this quantity. This is separate from that. And the angle comes out to be 47 degrees. And since we drew our angle like this, we would say something like this. And this just represents that corner of the triangle where we solved this theta from. And so that's this AC value is equal to AD, since this is one solid piece that doesn't move. So we can then just say AD is this quantity. Questions on this? If no questions, we can move on.
Wait, so how is AC equal to AD?
Okay, so AC is equal to AD because in the problem they say that arm CD remains vertical. So that what that means is that this piece right here, I'll draw it. You see over, I just want to make sure that I'm not writing off camera. Yeah, so what that means is that we have like the end of it where this is C, and then this thing that represents D. What that means is that this whole piece right here moves as one stationary thing. So as C turns this way, and C is now lower, CD still looks like this. And so this whole object here has the same acceleration. The acceleration at C is the same as D because this is like a rigid piece that doesn't turn. It remains vertical.
Okay, okay, thank you.
No problem. Okay. So we can go ahead and move on to the next one. So we're going to go to problem 2. It's an ICZV problem. And the problem has a structure. That has 2 members. To actually label this D. Whoops. They label this as D, where this is a fixed point that goes up to here, where this is pinned, goes down into a slider that lays on the ground. We're given that this is 45 degrees, and so is the other side. And that this is 90 degrees. And we're given that block D moves with a speed of 3 meters per second. VD, where VD equals 3 meters per second. And it says, using the ICZV method, determine the angular velocities of links BD and AB at the instant shown. So we're looking for angular velocity of BD and AB. So angular velocity of both of these pieces. So what we can do first is we can see that this is basically a rapid with a fixed point and a member going all the way up here. So we can draw our velocity perpendicular to the end of the rapid stick, just as you would normally. We can label this as VB. And we have our VD line over here already. So we have our 2 velocities drawn to start off. And omega AB. Omega BD. So what we're going to do is draw all the way out from these velocities. You draw perpendicular from the velocities, and where those lines meet is your ICZV. And then we can basically treat these 2 dotted lines as their own new raphistics, starting from the same center. So we know this velocity, right? So we can say we have a raphistic like this, 3 meters per second. And we can find this distance, and we know that, or we don't know, this omega value here, omega ICZV. So knowing that both of these lengths are 0.4 meters, given in the problem, I'm just gonna write it here, know that it's the same for BD as well. We can find the lengths of these 2 pieces. So this is just going to take a little bit of geometry. Getting some pop-ups real quick. Okay, we're good. Okay, so I'll redraw the triangle. It looks something like this. We know that this is a right angle, and because this must be a right angle, this has to be 45 degrees, and therefore this has to be 45 degrees. Because along the horizontal here, from the horizontal to our member, we know 45, and if this is vertical, the whole angle has to be 90, so 90 minus 45 is 45 for this side. And we know that this distance is 0.4, and if we have a right triangle, we can now use our trig functions to find the other lengths. So starting from, yeah, this would be our hypotenuse. Okay, so starting from this angle, we can say tangent of 45 is going to be equal to opposite over adjacent. Opposite adjacent, so our unknown, I'm just going to call this x, our unknown x over 0.4. You can multiply 0.4 over to solve for this length, and you get 0.4 degree or 0.4 meters. Now, real quick, we can know that that makes sense, that they're the same, because if these angles are the same, the corresponding sides have to be the same as well. So then we could say, using this same angle, sine of 45 equal to opposite over hypotenuse, 0.4 over hypotenuse. I'm going to use h for hypotenuse. So then h, you multiply that over, divide by your sine. So you're doing 0.4 divided by sine 45. You can solve for the height or the hypotenuse value, which is 0.566 meters. Yes, okay. So now that we have our ICZV triangle, its sides determined, we can go back over to our raphistick, and where we have our velocity at d, where this is fixed, our radius here, we now know r equals 0.566. And on a raphistick, we know that velocity is going to be equal to omega r. So we can say 3 is equal to our unknown omega, which is 0.566. And now omega of ICZV, this omega, we have solved for it to be 5.3 radians per second. And I can know that this omega value is moving counterclockwise, because if this velocity is moving to the right, this raphistick must be turning this way. It must be turning this way. With this velocity going this way, the raphistick must rotate counterclockwise. So that's how I could assume the direction. So then, moving to the other side here, where we have VB, we now know this omega ICZV value, because from here to here, it's going to be the same. We're moving about the same point. So we can say VB is equal to 5.3 times the radius here, which is 0.4. So VB comes out to be 2.12 meters per second squared. or meter per second. Yeah, meter per second. And so we've done this to get VB. And what we can say now is that omega AB, so from here to here, is going to be equal to VB times this distance. So if that's the case, what we say is VB, so 2.12 is going to be equal to omega AB times 0.4. And if you notice, this is the same as this. So our omega value is 5.3 here. And then just to prove it, we can go and do the same thing for VD, where we say that VD is going to be equal to the omega times this distance. So up here, we're going to have VD equal to omega BD times RBD, where VD was the 3 equal to the unknown omega. Sorry. Sorry, all of our numbers are right so far. I think I just skipped over one step on accident. Okay, there it is. So everything for our omega AB is totally fine. Everything for what we've done is totally fine. I just, like I said, I just missed one step on accident. So what they say is after finding this R from D to ICZB value, you can immediately say that the omega from B to D, so the omega here, is equal to your velocity, 3 meters per second, over the radius that we found from here. And all that is the same as what we have here. So this is just the like the proof from ICZV to here that this value is equal to omega BD. And since the problem was asking us to find A to B and B to D, the omega values for both, that's it. So any Sorry if the ending was a little confusing there because I tripped over myself a bit, but any questions on that? Alrighty. Then we're gonna jump a little bit and go to problem 5. So problem 5 states that there is a gear with a given angular motion, and we need to determine the acceleration of a point and the link's angular acceleration at the instance where the omega AB is 0. So I'll go ahead and draw this out. This is actually not connected in the center, but further down. Okay, so we're given information about the wheel, omega wheel, alpha wheel, where omega of the wheel is equal to 6 radians per second. And alpha of the wheel is equal to 12 radians per second squared. We know that from the center of the wheel, which is more like right here, that distance, r is equal to 3 inches. And from the center to where the member is connected, that distance is 2 inches. The entire distance of this arm is 8 inches. And we know that from the arm to this beam is 60 degrees. Okay, so that's everything we're given. We know right away that this wheel is going to be GPM, and B, this slider here, is going to be translation. We'll label this as A. That point is A, and the center is O. So AB is also going to be GPM. So we are asked to determine the acceleration of point B. Just letting someone in. We are asked to determine the acceleration of point B and the link's angular acceleration at this instant where omega AB is 0. So we can go ahead and draw out our acceleration equations, our relative acceleration equation, I should say, where we start off by saying that A is equal to B plus A relative to B. So we're starting from here saying that A is equal to B plus B relative to A. Or A relative to B. There we go. which is equal to B plus A relative to B. Wait, what? Oh, sorry. Acceleration A here is going to be equal to acceleration of O plus acceleration of A relative to O. O being the center, A being where the arm connects to the wheel. And that is equal to acceleration of B plus acceleration of A relative to B. So this is what we had written, but they have it O and then B. So I just wanted to have it the same as the solution. We can then go down a line and we can say acceleration of O. Since we see that the wheel is turning this way, given to us by the angular velocity and the angular acceleration, we can say that our acceleration at O is going to be straight to the left, since we know it's moving left. And we can know what that value is, acceleration at O, because we're given the angular acceleration, 12 RPS, and we know what the what the radius is here. So we can go ahead and say that the acceleration is our alpha value times that R. So that's going to be 36. Yeah, 36 inches per second squared. That comes from alpha value times the radius, 3 inches. Then we have the A relative to O. So here we're going to treat O as though it's a fixed point. So we're going to have a raffia stick that looks something like this, with a fixed point going down from O to A, with an AT and AN value. I draw AT going to the right because if the raffia stick starts in the center and goes down to A, with the wheel turning like this raffia stick must then rotate counterclockwise. So that's why I draw AT going this way. So A relative to O is going to have the same omega and alpha as the wheel because it exists relative to the wheel's center. So that's important to note. And we know that this radius is 2 inches. So right away we can say AT is equal to alpha R. So alpha 12 times R. So that's 2 inches. So 24 inches per second squared. And AN is going to be equal to omega squared R, where omega is 6. So that's 36 times the radius. 36 times 2 is 72. So that's how we know these two portions. So we can say equal to acceleration at B. We know that acceleration at B is going to be perfectly this way to the right because it's a slider locked into left and right movement. And we know, funny enough, you would think that if this arm were connected to the center, as the wheel moves this way, B would move with it as well. But since this arm is off center and below it, as the wheel moves this way, this centerpiece is going to move upwards. And as that move upwards, it's going to have to force B to the right in order to keep its stiffness. So that's why we say AB is going to the right. So then we'll have plus the raffia stick for A relative to B, where we treat B as a fixed point. This is B. Down here is A. It's A, AN, and AT. So we were told at the beginning that initially omega AB is 0. So we can say AN right away is 0 since AN is omega squared R. And then AT is unknown because this angular acceleration of AB is unknown. So we'll say AT is just equal to the unknown alpha AB times 8 inches. From there, it's just like the others where we can say we have knowns, both of these are known, one unknown, and a second unknown. But using some of the forces in X and some of the forces in Y, we'll have 2 equations, 2 unknowns, and we can solve. So we'll start off with some of the forces in the Y, giving us 0 from this portion. This is perfectly horizontal, so AT is not going to contribute. AN is going to be added, so plus 72. That's equal to 0. Plus, with this being 60 degrees, we would have the sine of 60 is going to give us vertical component. So we'll say plus alpha AB times 8 inches times sorry, they say cosine. Why do they say cosine? They do say cosine in the solution, but cosine of this angle would give us the horizontal piece. If this is sine would be opposite over. Oh, yeah. That makes sense, I'm pretty sure. Okay, so it should be cosine because when you do cosine of this, you're going to, it's not, they're not doing cosine of this angle, I'm pretty sure. So you would represent it like this, right angle, AT, 60 degrees. What you can do instead is knowing that this is 30, this must be 60. That's 90, this is 30. So that's might be kind of confusing, but basically all we've done is we've turned it into a triangle that looks like this with AT being here. And now this angle is 60. So cosine of 60 is the vertical component. Because with this original setup, the angle that we have is not going to be relative to AT. So we want to turn it into something that looks like this. So that's why we say cosine 60 degrees. So this setup, we only have one unknown, alpha AB. Where alpha AB is 18 radians per second squared. Then next we could do some of the forces in the X. That's going to be minus 36 plus 24 equal to plus AB. And minus sine of alpha 8 inches. So minus alpha AB times 8 inches times sine 60 degrees. Sine coming from here to give us the opposite horizontal component. Alpha AB is known, and therefore we can solve for AB and say that AB is equal to 113 meter per second squared. And since the question was asking for the acceleration of point B, there we go, and the length's angular acceleration, there we go. Those are our two answers. It is worth noting that this should be said to have a direction. And this should also be to the right. There we go. So, any questions on that?
Okay, so why again, like, did they do cosine? Because like
This piece.
yes, but for your drawing, the triangle on the top right, like, wouldn't you draw it so that it's like the 60 degrees is in the top right, and then the right angle would be on the left corner, because you would draw like it like a just a straight Y, if that makes sense.
Nice. Yeah, so I get what you're asking. So this is like perfectly horizontal. This is just the this member basically represented, and here's the arm with 60 degrees, right? So we have a shape that looks like this, 60 degrees. But the side that we care about is right here. This is AT. So this angle is not going to give us anything. I kind of overcomplicated it by doing it like this, because in the solution, he doesn't do it like this. He doesn't show these triangles, but he ends up with these answers. And this is the only way you get these answers. What you could do instead of this is just know that this is 90 and know that that's 30. So actually, sorry, you have to do these triangles, because when you set up this triangle doesn't have a vertical component. You see what I mean? It's just horizontal and two angles. So that's why they change it to be like this. And so then you have a Y and an X. And you get this triangle just by knowing that this is a 90 degrees. And so if this is 30, this has to be 60. We force this to be 90 by doing a vertical and a horizontal, and a 90, 60, this has to be 30. So you basically just make this triangle off of the original triangle, and you can use this to get your cosine 60 and your cosine 60 and sine 60. So I know that's kind of roundabout, and the solution that he has posted for this problem doesn't show these triangles, but this is what he's doing.
Okay, thank you. Yeah, that perfectly answers my question.
Cool. Okay, so we are making pretty good time so far with all the questions that I want to get through. We are just about halfway in only an hour. So next we're going to jump to problem 7. And this is going to be a, what's it called? In one of those problems where you have a shape with part of it missing, and so you have to use the table to do the IG stuff. The name is just escaping me right now. Sorry about that. But yeah, so problem 7. We're given a circular disc that is pinned as shown at A. With a square in the center. The diameter of the circle is 12 inches. And the square dimensions what does it say the square dimensions? It gives us that the thickness of both the circle and the square is 0.25 inches, so very thin. And it tells us that the density of the material, rho, is equal to 0.013 slugs per inch cubed. Okay, yeah, there it is. So it tells us that the dimensions of the plate are 4 inches and 4 inches. That's what I've been looking for. Okay, so from that, we need to find the mass of our two shapes, and then we can go from there. So I'm going to draw out the chart. We have shape. We're going to put the circle on top and the square on the bottom, followed by mass. Okay. And the IG. MD squared. And then finally, IG plus MD squared. So the mass of our circle is going to be calculated using the density and a found volume. So if we know volume of circle is going to be pi r squared as the area times the thickness. So radius of the circle is going to be half the diameter, 6 inches. So it's going to be pi times 6 squared times 0.25. Where this comes out to be, volume of circle is equal to 28.26 inches cubed. And knowing the density of the material, we can find the mass of the circle by doing the density times the volume, because density is mass over volume. So the mass then comes out to be 0.373 slugs. Volume of the square, of course, is going to be the same area times the thickness. So 4 times 4 times 0.25. Volume of the square comes out to be 4 inches cubed. And therefore, mass of the square is the volume times the density. And we get 0.0528 slugs. These are our first two answers for the chart. So we have 0.373 and 0.0528. Our IG values then are going to be found using equations that you guys are given the IG equations on an equation sheet, right? Okay.
I think so.
Okay. Yeah, I would be shocked if you weren't. Yeah, so IG for the disk or the circle. So IG for circle is equal to 1/2 the mass times the radius squared. You are? Cool. Yes. So IG for the circle, 1/2 mass times radius squared, comes out to be 6.714 slug square inches. So that's and IG for the plate or the square is equal to 112 a squared plus b squared times m. So plugging in a and b is just the dimensions. Mass is what we found before. You can solve for IG of the square as 0.1408 slug inches squared. And so these two values are what we need next. So for the circle was 6.714 and for the square is 0.1408. We then need MD squared, where D is going to be the distance from the point. This is where the axis that it's rotating about moves through the page to the center. So for both of them, the value is 6 because the diameter of the whole circle is 12. So this is just the radius because this point is on the very edge of the circle. So MD squared is going to be, for the circle, the mass times 6 squared. So for the circle, it comes out to be 13.43. And same for the square, the mass times 6 squared comes out to be 1.9. Then IG plus MD squared is just the sum of these columns. So 20.142 and 22.2. Wait. No, 2.04. I read that. 2.04. Yeah. It's just this plus this equals this. So then the entire question is asking us for determine the moment of inertia of this disk in an axis perpendicular to the page. So the way this question works is that this square was not said to be a hole. This square was a plate on the circle. So this is an extra mass. So both of these are positive. If this was a circle with a square hole through it, then you would have a negative value on the square. But because it's two pieces that are fixed together, we have both positive. So our final answer of IA is going to be equal to this plus this, where we can say that IA is 22.2 slugs inches squared. I want to make sure that the camera actually sees all of this. Yeah, gets all of it. So this is just saying IA is equal to 22.2 slug inches squared. And once again, if this were a hole, you would just have a negative value on the square, and you would do this value minus this value for your total. So any questions on this? Any questions from you guys? I know you kind of just dropped in, but.
What topic is this?
This is moment of inertia. Yeah. Questions from the Zoom?
Are you recording it?
Yes. Yeah, and we're making pretty good time too. We're already halfway through all the questions I had picked out from the review. Yeah.
What time did you start?
Just after 1.
So you got here yourself as well.
All right, if there is no questions, I'll go ahead and move on. Yeah, I'm just pulling out, I pulled out 8 problems from the review to do. We've done the first 4 so far. We did problem 1, problem 2, problem 5, and problem 7. And then we're gonna go over problem 8, problem 11, 12, and 16. I tried to pull one from every category or topic, and we seem to have plenty of time. So we'll go ahead. Problem 8. And 8 is going to be a force acceleration, I think is what it's called. Okay. So we're given a cord wrapped around a core where we have a wall, kind of comes out into our circle. And this circle has an inside layer. So it's like 2 circles on one. Where on the inner circle is a block that hangs down called block B. The radius from the center to the inside is 1.5 feet. And the radius from the center to the outside is 2.75 feet. We are given that the block weighs 5 pounds. The whole thing starts from rest, and we are asked to determine the acceleration of block B and the tension in the cord. Yeah, that's what we're asked. And so the spool, aka the circle, has a weight of 180 pounds. So this thing is heavy. And the radius of gyration about the axle A, where A is the center. Yeah, so the radius of gyration about the axle A, KA, is 1.25 feet. Okay, so in order to solve for the acceleration of block B and the tension in the cable, we're going to set up a free body diagram for both the circle and the block. So we'll start off with the spool, where we have our free body diagram showing all of the forces acting on it. So we're going to have 130 pounds going down, or 180 going down, because that's the weight of the thing. We're also going to have an AX and an AY, because this is a fixed point. And out from the center to the inside part of the circle, we're going to have T. Then on our other diagram for the circle, where we have FBD and KD, the center A here, and the wheel is going to spin this way with T pulling down on the right. It's going to cause it to spin clockwise. This is going to be IG alpha. We can then set up the same set of diagrams for our block. We have FBD for the block. £5 and tension. This is just the weight going down and tension going up from the cable. And that's going to be equal to KD for the block, which is going to be mass times AB, moving it downward. Peace, bro. Thanks. Okay, so now that we have our two sets of diagrams, the spool and the block, we can start off with a sum of the moments about the center of the spool. So we can do sum of the moments about A equal to the AX, AY, and weight are all going to cross off because they all pass through the center. So we're just going to have this equal to T times the distance from the center to where the cable is, which is 1.5 feet. And that is going to be equal to our IG alpha. So we can say that IG for the spool is equal to, and this is just a formula we know, MK squared. So we know that mass of the block, or mass of the spool, is going to be its weight, 180 pounds, divided by 32.2 as the gravitational constant. It's 32.2 because we're in US units, and 9.81 would be for metric units. This times 1.25. So our IG value would come out as 8.73 slug feet squared. We can take that and plug it back in here. And then we have our first equation set up. We can move on then to the block. And we can see in the block's case, we're only going to have a sum of the forces in Y. This is because there's only forces acting in the Y direction. So we're going to have T minus 5. T going up, 5 going down is equal to minus MAB. Mass of the block we know can be 5 divided by 32.2. And we know, yeah, so we can say mass is equal to 5 over 32.2. And we can say AB is going to be equal to alpha R. And we know that from here. Where our R value is going to be 1.5 from here, because basically what we're doing is we can say the acceleration here is the same as the acceleration here, which can be treated as a rapistick from A to this point. And so that's how we know we can use AT, because I'll draw it real quick. What we're saying is that we have B is the same as the rapistick here, with this being A and this being the point where the cable meets the wheel. And so this acceleration would be AT, and AT is alpha R. R is, in this case, 1.5 feet, known from here. So combining AT being alpha times 1.5 and M being 5 over 32.2, we can say that AB is or can be replaced at least with minus, because this is minus, it's moving down, with minus 0.233 alpha. And so this 0.233 just comes from 5 divided by 32 times 1.5, because we're just putting that all together in here. And then that is our equation here. So we have T minus 5 is equal to minus 0.233 alpha. And if you see now, we have T and alpha and T and alpha. We can solve this using a matrix. So we'd have 1.5 T minus 8.73 alpha equals 0, and T plus 0.233 alpha is equal to 5. And that just comes this equation here, this equation here. You can use a matrix for this and say that T is equal to 4.81 pounds and alpha is equal to 1.23 feet per second squared. And you would say going down. Sorry, I skipped one step. My bad. You'd say alpha, so this is our first answer. Well, you don't need that. You'd say alpha is equal to 0.826 radians per second squared. So then you could take alpha back over to here, where we have AT equals alpha times 1.5. And we can then say that AB from here, because AB is going to be the same as AT on this Raphisic, because this is one continuous cable. So AB here is going to be 1.23 feet per second squared. And these are the answers that we were looking for. Any questions on this? All right. Okay, so we're going to go ahead and start with problem 11. This is going to be an impulse momentum problem. And so we have a block set up on a pulley attached to a wheel with an inner and outer radius, with the inner radius being set on a surface. So we have, I'm pretty sure Dr. V talked about this problem at the end of class, but his explanation was kind of, it was good, but it was fast. And so I wanted to go over the problem again. So that's 2 feet. That's 1 foot. So the outer radius is 2 feet and the inner radius is 1 foot. The block is labeled as B. The wheel is labeled as A. This problem says the inner hub of the wheel rests on a horizontal track. Determine the speed of the 10-pound block 2 seconds after it is released from rest. That's how we know that it's impulse momentum. It wants us to determine the speed of the 10-pound block 2 seconds after release from rest. So 2 seconds from rest. Speed 2 seconds from rest. So that told us that the block was 10 pounds. We also know that the wheel has a weight of 30 pounds. And a radius of gyration of 1.3 feet. So our K value here is 1.3 feet. I'm gonna just let you know we're working on problem 11 from the dynamics review. And we also know that mu sub s is 0.2. And mu sub k is going to be equal to 0.1. We're going to assume a no-slip wheel, and at the end, we're going to verify that assumption. So right away, we know that this wheel is going to be GPM, and the block is going to be translation, just moving in one direction. So properties that we'll need to identify right away are the mass of the wheel and the mass of the block. So I'll say mass of wheel is going to be equal to 30 pounds divided by 32.2, the gravitational constant for US value, for US units. So mass of a wheel is 0.932 slugs. Mass of the block is going to be 10 pounds divided by 32.2, which comes out to be 0.3106 slugs. We can then know that IG of the block, or IG of the wheel, I should say, is the mass of the wheel times K squared. IG equals MK squared. So M being 0.932, K being 1.3. We can solve that and know that IG for the wheel is 1.57 slug feet squared. So now we can set up our diagrams for the block. So we'll say our initial diagram starts from rest, 0, plus the integral from 0 to 2 seconds of the block, where we know that this value here, this tension value, goes up as T, and the weight of the block goes down as 10 pounds. That's going to be dt and equal to mvb, mass times velocity of the block. We know that's going down because this weight is going to pull this way, the wheel is going to turn, and that's just how the system is going to move. So using that equation, or using these diagrams, we can develop the equations 2t minus 20. We get this from doing t minus 10 from 0 to 2. So 2 times t minus 10 minus 0 times t minus 10, 2t minus 20. And that's going to be equal to, we know what the mass is. And VB is unknown, but we can rewrite it. We can rewrite it as 3 omega of the wheel. And so we know that we can rewrite it like this because the velocity here is going to be the same as the velocity here. This one big cable means that this V is equal to this V, which is equal to this V. So VC is equal to VB. And if this is true, then we can imagine that a raphostick would form here, where we can imagine this is fixed, and this would go straight up, where this velocity is equal to omega r. R being 3 feet, 2 feet up, 1 foot down from the center. So that's where we get 3 from, and then the omega value is unknown. That's why we just say omega of the wheel. So we can write this as 2t minus, sorry, this should be minus here because this is moving down. So 2t plus 0.932 omega of the wheel is equal to 20. So this is our first equation. Okay. We can then move on to our wheel, where once again, the wheel initially is going to be 0 because it's at rest. So that's going to be plus from 0 to 2. The wheel, where we have a normal, I'm going to draw the inside portion of the wheel too. We're going to have a normal force, a friction force. The point of contact I will label as right there. That's the point of contact. It is the same as the fixed end of the raphostick, with tension acting on the top and the 30-pound weight acting down the center. That's going to be dt, and equal to mvg, mass times velocity, from the center, because this wheel is going to be moving to the left. And it's also going to be spinning. So we're going to have Ig alpha. So what we can do here is we can say some of the moment, we're going to use counterclockwise as positive. We're going to say some of the moment about the point of contact. And what this does for us is it allows us to get rid of friction, which we just don't really want to worry about. So we're going to have 0 for the first part. That's going to be plus the integral from 0 to 2 of t times 3, because once again, this distance here is 3 from the top where t is connected down to the point of contact. So we're going to have 3t. That's it for this piece, because the normal force, friction, and weight are all going to pass through the point of contact and therefore not be included. So 3t dt, and reminder that big T and little t are not the same. Big T is tension, little t is going to be time. So that's going to be equal to Ig omega of the wheel plus mvg, since we said counterclockwise about this point. As this comes around, mvg is going to be positive, and the distance there is going to be 1 foot. So we then know what Ig is, and we can solve this and say 6t Yeah, 6t is equal to 1.57 omega of the wheel plus 0.932 VG, where 0.932 is just the mass of the wheel.
It wasn't that bad. I got 74. 74? I'm not mad.
So from there, we can combine our equations. We can say,
He was like, oh, I was like, oh.
oh, right, that's how they say this. So from here, we can replace VG. We can say VG is equal to omega of the wheel.
When I tell you,
We know that that's true because
when I tell you the last part,
VG starts here in the center. And if the point of rotation is here, the radius is 1. So what we're saying is omega r, but r is equal to 1. So we can just get rid of it. And we can just say this. So in our equation 2, we can replace VG with omega of the wheel. We can then combine these two and say 6t minus 2.5 omega of the wheel is equal to 0. So then we have our equation 1, our equation 2. You can set this up in a matrix with 2, 0.932, 20, 6 minus 2.5, and 0. You can solve these and find out that t is equal to 4.72 pounds, and omega of the wheel is equal to 11.3 RPS. And that's going to be counterclockwise.
Because I get so ready to turn it in, and that would take the most time because I have to check everything else in the drawing.
So then the question asked us to determine the speed of the block. So knowing what we do, we can say that VB is equal to omega r. Where VB is going to be equal to our omega value of the wheel, 11.3, and the r value of 3 feet from here to here. So that comes out to be 34 feet per second down. So that's the answer that the question was looking for. And then the last thing we would need to do is check the no-slip assumption. So in order to do that, we would set up some of the forces in the x direction for this, where we would have the tension and the friction, and that would be equal to minus mvg. So plugging in the values, we would just be checking to see if the friction was greater than F max. So the friction that you would find in this problem would be 0.55 pounds, and F max would be our mu sub s times normal force, which normal force here is just going to be equal to the weight. And so the friction force you would find is 0.55 pounds, which is less than the friction max, which is 6. Therefore, our no-slip assumption is good. Any questions on this problem? All right.
Hey, Mike, I have a question.
Oh, sure. What's up?
So you chose to take the moment around the point of contact so that you could eliminate those 3 other forces?
Yes, exactly.
So you could have done it around, the center of that disc?
Yeah, if you had done the center, you would have needed to include friction in your moment equation.
Okay.
And so as long as you do that, which you can find the friction value by doing mu sub s times the normal force, which you know that the normal force is just going to be the weight because these are the only two y direction forces acting here. So you would say friction is equal to mu sub s times n, where n is 30 and mu sub s is 0.2. That would be your friction value, and you would need to have that in your moment equation.
Okay. All right, thanks.
No problem. Any other questions before I erase? Alrighty.
When I took this class, I was I thought this class was, interest engineering? Yeah, I really thought it was that class was like more intense. And I didn't know we were doing that. So like I walk in and I see all these problems. I'm like, what? It's so hard. Yeah, and the week off next week, so everybody does. And I played science. Yeah, I played geometry visualization and the first part? Yes. And then I'm a discipline like chemistry minor, so I will be doing geometry classes center. Wow, that's cool. It's gonna suck. It's gonna kill me. I hate chemistry. Like the only thing that's literally holding me back is I'm supposed to be pre-med. I literally Orgo 2 is the only thing that's making me. Orgo sucked.
Okay, so then we can move on to problem 12, a work energy problem.
And like the way my schedule is
So we are said that we have a system with a wheel with an inner and outer radius. The center of the circle is connected to the wall by a spring. And the inner radius is attached to a cable that goes on a pulley. That goes up to another pulley. That has a block hanging from it. What's up?
Would that just be one, like would the tension be the same to just one cable? Correct?
Yes, so it's still good. That's a good question. So this is one giant continuous cable. So the tension value in this cable, no matter where you cut it, no matter what diagram you're looking at, it's just T, no matter what.
Where's the Orgo 2?
Where this is labeled as G2. We have the point of contact down here. We have an initially unstretched spring. We have the outer radius is 6 inches. And the inner radius is 3 inches. They label this point as G1. This is G2. And like was previously asked, this cable is one big cable, so it is T everywhere in it. It is the same tension value. So we are said that system is released from rest in the positions shown below. So it starts from rest, and we are asked to determine the angular velocity of the wheel once the block has fallen 1 foot. We have a 20-pound wheel. It is told that the wheel is no slip, so it is given to us in the problem. We are told that the radius of gyration is 4 inches about its center. So K is equal to 4 inches. And there's a cable wrapped around the inner radius, passes under and over 2 small frictionless pulleys, so we don't need to worry about friction on the pulleys, and is attached to the 50-pound block. Oh, does that say B? Yeah, it does say B, not G. Where this is 50 pounds. So B1 and B2. The spring constant K is 90 pounds per foot. Is initially unstretched at a length of 13 inches. So the spring is 13 inches from the wall to the contact point on the disc, and there is enough friction to prevent slipping. Note that IG equals MK squared. So what are we asked to find? We are asked to determine the angular velocity of the wheel once the block has fallen 1 foot. So we're looking for omega of the wheel after B2 goes down 1 foot. Times 50 pounds, yeah, okay. So once again, what we can solve for first are the masses of our wheel and block. So we can say the mass of the wheel is going to be the weight divided by 32.2. So mass of the wheel comes out to be 0.621 slugs. Mass of the block, which I'm just going to say mass of B2, is going to be 50 pounds divided by 32.2, which is 1.55 slugs. We also know we can express this K value in terms of feet because that's the units that that some of our other things are given in. So this is going to be 1/3 of a foot. And we can say 6 inches here is equal to 1/2 a foot, and 3 inches here is equal to 1/4 a foot. So having consistent units is important. And 13 inches. Is 1.083 feet. So next we can solve for our IG value, where we say IG is equal to MK squared. M is the mass of the wheel. K is given to us as 1/3 of a foot. Or wait.
I'm pretty sure our like yeah. The only thing I know is that it's like a special table.
Yeah.
Yeah.
So IG comes out to be the mass times 1/3 foot squared. IG comes out to be 0.069. 69 slug feet squared. So we need to calculate the work on the spring and the block. So we know that is going to be equal to minus 1/2 times the spring constant times S2 squared minus S1 squared. Where in this case,
I'll see you later, guys.
the spring is unstretched. So therefore, our L naught and L1 or Li, I'm not sure what that says, but L1, I believe, is going to be equal to S1, and S1 is therefore 0. So because this is unstretched, that's 0.
Wait, so why is that 0?
Because the spring is unstretched. No problem. So the block falls 1 foot, and therefore our S value moves 1 foot, where we can say that
Isn't the formula for like S sub 2 and like S sub 1? So for S sub 2, isn't it the length L sub 2 minus L sub 0?
the length of the formula for which one?
For like S sub 2 and S sub 1. Isn't there a formula for it?
There is.
Yeah. Do you know what those are?
I don't know off the top of my head.
I can look at it.
I know there is a formula for it.
Yeah, there definitely is a formula for it, which,
Just given that to us in the exam as well. I know
Okay.
some little sheets that we got that we get.
okay, well, that's pretty good then. But yeah, so just, if the spring is unstretched, then S sub 1 is 0. And then S sub 2, you still have to calculate.
Okay, but what would be a time when F sub 2 would be 0?
What would be a time when S sub 2 is 0? If I don't think you would ever need to worry about that, but I imagine if it said that after the motion, the spring is considered unstretched, then S sub 2 would be 0.
S sub 2 is L2 minus L0.
Mhm.
S1 is L1 minus L0.
That's fine.
Right, so in this case, if we have S1 equals L1 minus L0, and S2 equals L2 minus L0, these are L's.
Oh, that's not weird.
Right, so both of these are 0. Therefore, S1 is 0. So here we know that L naught is 0, but we don't know what L2 is. So we need to find out what L2 is. So we'll start off by saying we can start off by saying SA. I should label this on the diagram, where A is the wheel, and down here is the point of contact. So we can say SA is going to be equal to theta RA. And we can rearrange this to say theta is equal to SA over RA.
Right now, taking help you with things.
And we can say that SA is 1 foot, because if this block moves 1 foot, the wheel must also move 1 foot. So that's 1 foot divided by RA, which in this case, R is going to be 9. What does that say? Yeah, 9 over 12, because that is the distance from here to here. So that theta value comes out to be 1 over 9 over 12 as 1.33, and that's radians. So we can take that and go into an SC and say that SC is equal to its own theta RC, where C is considered to be the center of the wheel. So here we'll say that SC, our unknown, is equal to the theta value, which is 1.33, times RC, which is from center to the point of contact, so that's 6 inches. So 6/12. So SC comes out to be 0.67 feet. And that SC value from here to here is the same as our S2. Because S2 is going to be relative to this spring, which is connected at the center of this wheel.
SA, is that like displacement? Is that like
Yeah.
how much is going?
Right here. Yes.
Okay, so that's one.
Yes, exactly. Exactly. So SA and 1. So SA is equal to theta RA. We rearrange it and say theta is equal to SA over RA. SA is 1. RA is 9/12 because from here to here, they're saying that A is the same as B1, I believe. So that's going to be 3 and 6, so 9/12. And they say 1 because this distance is going to move 1 foot, just as this distance moves 1 foot. So that's how they say this is the same as, that's how they solve for SA. And then they use that theta value with RC from the center to solve for SC, which is the same as S2, because that's where our spring is connected. So K here is going to be the 90 pounds per foot times 0.67 feet squared. And U for the spring is going to come out to be minus 20 foot-pounds. So we can go to the block, and we can say that for the block, we're going to have another U equation, which is equal to minus the weight times delta Y. So that's going to give us U is equal to minus 50 times 1 foot. And so it's just, sorry, that should be times minus 1 foot because it's moving downwards. If it were moving up, we would say 1 foot, but because the relative motion is down, we say minus 1 foot. So U comes out to be 50 foot-pounds. And that's for the block. So then the total work, sorry, I should say for the block. So total work U is going to be the block plus the spring. So that's going to be equal to 50 plus minus 20. So total work is 30 foot-pounds. And the question is asking us for, going back to it, the question is asking us for the angular velocity of the wheel. So now that we know the work, we can move into energy, where we say that it starts at rest, so our T1 is 0. So right away we can say T2 is equal to 1/2 the mass of the wheel times the velocity of the wheel squared. Mass of the wheel we found here, velocity of the wheel.
Isn't there also like angular velocity and stuff like that we have to deal with since it's turning?
Yes, I meant to write a plus sign here. Sorry. So it's going to be, yeah, so mass of the wheel is here, velocity of the wheel currently unknown. So we're going to have plus 1/2 IG, which we found here, times the angular velocity of the wheel squared, which is what we're looking for. There is a lot to learn.
My brain hurts just looking at it.
Yeah, I need at least a 63.75 to get a base 70 class, and that's what I want.
Then we're going to have plus
And I swear if 90% of the class does not do the SPY, I will go.
1/2 mass of the block,
Because I can't afford to.
which we know from here, times velocity of the block squared. Okay, so we know the masses for both, we know the IG for both, but our velocities and our angular velocity are unknown. So what we can do is we can say that velocity of the wheel is equal to velocity of G, the center, which is equal to omega of the wheel times R. So we're saying that velocity of the wheel is, what we're saying is velocity of the wheel is equal to omega of the wheel times R.
At the beginning.
So the velocity here at the center is going to be equal to omega times R.
I know, I have physics 2, top 2, and then the class. And then all the
So yeah, velocity is equal to omega times R, sorry. And so then this one is already in terms of omega. And then velocity of the block is going to be equal to omega of the wheel, but times a larger radius as the raffle stick extends all the way up to this point. So we have a smaller raffle stick from point of contact to the center and a larger one from point of contact to where the tension cable meets the wheel.
I don't understand people having like finals parties, you know, like what's the point of studying?
I was up for 2 hours. because they
So
were not-
plugging in everything we know with substituting V for omega R and V for omega R, with these being the same omegas as right here, and the R values just being 6 and then 9 inches. So 6 inches and 9 inches, make sure those are in feet. You solve all of that, and I'm running out of space, so I'm just explaining that V is omega R, V is omega R, that's how that comes, and you would plug in everything we know, the mass is the IG, the mass, and you'd say T2 can be written as 0.549 omega of the wheel squared. And then we know that based on the work energy relationship, we can say T1 plus U from 1 to 2 is equal to T2. And so all that means is that T1 is 0, like we said at the beginning. U is 30 foot-pounds, equal to 0.549 omega of the wheel squared. Divide that over, square root, and omega of the wheel is equal to 7.39 radians per second clockwise. We know that it's clockwise because the wheel, as this block turns, or as this block falls, is going to rotate right, which is a clockwise rotation. That was a long problem, different from all the rest of the ones that we did. So any questions on this? Any questions in the Zoom? All right, go ahead. Okay, so next up we have problem 16 from the dynamics review, and this is actually the last one I had planned to cover today. This went significantly faster than I was expecting. So problem 16 shows us a slant with a block on the horizontal, a pulley here with a cable connecting to the block, and a cable connecting to the center of a wheel. With the radius of the wheel being 100 millimeters, the center of the block referred to as G, with the block itself referred to as B, and the wheel referred to as A. The angle here is 60 degrees, and this is horizontal. So it says the cylinder A has a mass of 50 kilograms. 50 kilograms. And a radius of gyration with respect to its center of mass of 70 millimeters. The cord is connected to the 100 kilogram block. Which rests on a horizontal surface, which rests, so that means this problem is likely starting from rest. The kinetic coefficient of friction between the horizontal surface and the block is 0.25, so that means that mu sub k is 0.25. If the cylinder rolls without slipping, determine the acceleration AB of the block, the angular acceleration alpha A of the cylinder, the tension in the cord. Okay, so we're looking for acceleration of the block. Yes, so we're looking for AB alpha A of the cylinder and tension. Okay, so right away, we can classify the motion. This is going to be translation, and this is going to be GPM. So we are given the masses, so we can find the weights of these. So we can say weight of A is going to be 50 kilograms times 9.81. So the weight of A comes out to be 490.5 newtons. The weight of B is this mass times 9.81, so 981 newtons. Then we can solve for IG. IG is mk squared, where m is the mass of the wheel, k is given to us as 70 millimeters. So IG would be 0.245. And you would change this into units of meters. So we would use 0.7 meters, 0.07 meters. So once we got all of our basic information, we can move on to doing our diagrams. So we'll do the wheel first. We have a free body diagram of the wheel. Here's the center. We have tension moving like this along the surface. We're going to have the normal force. We're going to have a friction. And we're going to have a weight of 490.5. That is going to be equal to the mass times the acceleration. And the IG alpha value.
My clear case, because you got a clear case, you can see through the machine. He's like, yeah, we want 5 pieces. Oh, okay, bougie man.
No, and then I was like,
Yeah. Like if I saw it, say that probably higher.
So we can get a few equations from this diagram. We can first say some of the moments about G, G being the center here. So that's going to be equal to the tension goes away, the weight goes away, the normal force goes away. We're just going to have the friction on this side. So that's going to be, since we're going clockwise and we assume friction, or counterclockwise and we assume friction this way, we're going to have minus 0.1 F. We say 0.1 because this distance here is 0.1 meters, given to us as 100 millimeters over here. That's going to be equal to IG alpha, where we can replace IG with the value that we solved for at the beginning.
Yeah, I literally walked on campus off the bus. Read the email.
We can then do some of the forces in this direction, which is just going to be parallel to this surface. That's going to be equal to T minus F, T and F, and then we're going to need the components of N and the weight. So the weight is just going to be sine 60, since we know that the angle here is 60 degrees. We know that the angle here is 60 degrees. So minus 490.5 sine 60. And then
his entire 200,000 salary.
They don't have N in this equation, and I'm wondering why. Oh, that's easy, because it's perfectly perpendicular to the direction that we're assuming, so normal force is not included. So then we're going to have the minus MAB, where we know that the mass is 50 kilograms. So we can go ahead and, yeah. We can then do our block diagram, where we have tension and the 981 newtons going down. We have a normal force, and we have friction. That is going to be equal to MAG. So from these diagrams, we can do some of the forces in the X and say F minus T is equal to minus MAG, where we know that M is 50 kilograms or 100 kilograms here. So we then have three equations, 1, 2, and 3. And we're going to have F, T, well, this F and this F, I believe, are different. Yes, F of the block is going to be here. So what we know is that FGH and FGX, or AG, this AG and this AG are the same because this cable connects them to the centers. So the AG values through them are going to be the same. As this piece accelerates, this piece must also have the same acceleration. So this one and this one are the same. And we know that FB is equal to mu sub k times the normal force of the block. With the normal force here is just going to be equal to 981. And mu sub k is given to us as 0.25. So FB is equal to 245 newtons. So we have solved for FB. So we can go ahead and say that this, we're gonna have T minus 100 AG is equal to 245 newtons. So this is one of our equations. We have this second equation and a third equation where T is the same from here to here. These F values are the same, so that's two unknowns. And then we have AG and alpha. We can express AG in terms of alpha because in this wheel, we can imagine a raffle stick where alpha of the wheel is equal to, or where AG of the wheel is equal to alpha R, because this acceleration here would be AT, which is the acceleration AG. So we can replace our AG values with 0.1 alpha. We say 0.1 because that is our radius, 0.1 meters. And now we have 1, 2, 3 unknowns in 3 equations. We can set them up in matrices with the T's lined up, with the alphas lined up, and with the F's lined up. And in a matrix, we would solve for T equals 348 newtons. F of the wheel is equal to minus 25.3 newtons, and AG, alpha because we expressed this in terms of alpha. Alpha would come out as 10.3 radians per second squared. And then we would plug that back into our equation with the Rafa stick, where we say AG is equal to alpha R, and our AG value would be 1.03. Meters per second squared. And that would be everything we were looking for. Any questions on this? Any questions from the Zoom?
I have a question, but it's not particularly well, I guess it can be like applied to this problem, but would you be able to explain like the difference between when we use mu sub k and then mu sub s, like what are the difference between those two, and in what circumstances do we use each of them?
Okay, that's a good question. So for this one, we know that we use mu sub k because it's the only one given to us. But for a different problem, like let's say they just gave us a random mu sub s value for this problem, you would know that you're going to need to use the mu sub k value, because in this problem, it is stated that the system is moving. So once the system begins to move, you want to use your mu sub k value. But while the system is at rest, you want to use your mu sub s value. So in a problem like, do you remember when you would test slipping and tipping and things like that? So in a problem where you have an object sitting on a surface and it's not moving, and you're looking for the values right before the object begins to slip along a surface. So let's say you had random block here and you were like, oh, it's gonna slip this way, but it's not slipping yet. And in this problem, what we're calculating is the exact like 0.0000001 seconds before it starts to actually move. So in that point where the block is on the ground still and nothing is happening, you use mu sub s for static. But in this problem, when things are moving, we have established that it is moving. And because we know that things are moving, we have to use mu sub k.
Okay, thank you.
You're welcome. So any questions on this problem before I erase? Alrighty. Oh, somebody unmute.
Yeah, so I have another question. It also does, like, I don't think it really applies to this, so you can erase it if you want to, but it just is like Dr. Badir is always going over like the slipping for the wheels, like a no slip wheel and everything. And he says that we can't assume it to be, like, we can't assume the force of friction to be a certain value until we like test it. So could we review like one of those problems? And
Yeah, for sure. So that's a good question, because a lot of people get confused about that. When I first learned about it, that was me as well. But it's actually less complicated than it seems. It's just a lot of engineering stuff. When you first learn it, seems like this weird thing, but that's just because you've never seen it before. And so having a second explanation will probably clear it up a lot. So that we actually went over a problem where we tested the slipping. Yeah, so I'm gonna go back to the problem I did before. I'm not gonna do out the whole thing again. It was problem 11. And what we did was we had to determine the speed of a block after it was released from rest. So I'll draw out the diagram again quickly. So it looked like this. With a pulley here. And so this wheel was moving on this surface. And this block was moving down and the wheel was going to roll that way. And so we went through the problem and we determined the speed of the block and we found everything. And then at the end, because this problem doesn't say explicitly that the wheel is no slip, if the problem says this wheel is no slip, or you can assume no slip on the wheel, then you don't have to worry about the verification. But the problem says if you assume a no slip wheel, you must verify your assumption. So all that means is at the end, we have to test whether the friction that is occurring is greater than, so I'm gonna write if friction actual is less than friction max, everything is okay. If friction actual is greater than friction max, that's bad. So we test that by knowing that the friction actual is solvable for in our problem, but we'll talk about friction max first. So friction max in this case, and this is a good example because this problem, this ties back into the question you just asked before this. So this problem says that everything starts at rest. So starting at rest, we know that we're going to use mu sub s because nothing is moving. So for F max, we're going to say it's equal to mu sub s times our normal force. So this is our F max formula for this because nothing is moving. If things were moving, our F max would be equal to mu sub k times normal force. So F max is going to be equal to the mu sub s value that was given to us as 0.2. It was found that the weight of the wheel is 30 pounds and there were no other vertical forces, so normal force has to be equal to the weight. So this was 30 pounds. So the F max was found to be 6 pounds. So now that we know F max, we need to find our F actual. So F actual was found, and this is a lot easier once you've written out the entire problem because you would have your diagram already ready to go. But in this case, all that's going on is you would have your diagrams from this problem, which I can write out because we need them to solve for it. So this was our first diagram with point of contact being here. So this is G. And so with these diagrams, which you get from taking this wheel and you start from rest. So the first circle that would exist is just 0, so you don't have to write it. The problem is saying that this block is going to move over the course of 2 seconds. So from 0 to 2. So we have the integral from 0 to 2 of the wheel turning with the friction acting here, the normal force, the weight, and T. So how we can solve for the friction that's happening here is we can say sum of the forces in the x direction is equal to minus F minus T equals minus MVG. And here that's going to get us, sorry, this is integral from 0 to 2 and integral from 0 to 2. There we go. So that's going to get us equal to minus the t value, which was found previously in the problem. So in the previous explanation of this problem, you can see where the t value comes from. So I'm going to write from 0 to 2 f minus from 0 to 2, and this is dt, of course, minus 4.72 dt. That's equal to values, once again, that were calculated in the problem, which were, that's going to be minus because it's moving to the left, 0.932, and VG was 11.32. So doing all of this and taking your sum of the forces in the x direction here, solving the problem, we end up finding T, M, and VG. So F is our only unknown. We can come back to this to test this and find our F actual is equal to 0.55 pounds. And that comes from just solving this out. And so then we have our F actual as 0.55 and our F max as 6. So F actual is less than F max and the wheel is no slip. If this value came out to be greater than F max, then the wheel would slip and that would be bad.
Okay, thank you.
You're welcome. Any questions on that, or was that clear enough?
Yeah, I'm pretty sure you like cleared everything up. Yeah, like any questions that I had about the and use of S, you answered those as well. So yeah, thank you.
Awesome. Any questions from you guys on this? Okay, so we went through all 8 problems that I pulled out of the review. There are 16 total, so there's still 8 other ones that you guys can work on. And if you have questions, feel free to email me. There's still just over an hour of time that I had scheduled for this. So if anybody has any other specific questions, we can go over that. Otherwise, I'm kind of just hanging out. Do you guys have any questions on anything you wanted to cover?
Not really, just more practice problems.
Okay, there's one question that I wrote down. It's from let me see. Okay, it's from Force Acceleration 2, like that module.
Okay.
And it's the like extra sample questions at the bottom, like the ones that are numbered like 17 dash whatever. And it's number 17-96, and towards the bottom of the solution it does like where it has like multiple equations to solve for something. It has that, and then there's a part where I think it's friction, the friction of A, so FA is negative, and I don't know why they put that, and I'm not sure if it's like a mistake or if I just don't get it.
Okay, so I got it pulled up. So you said 17.96?
Yes.
Okay, so where they have the where they have the 1 and 3 equations labeled and it's like solve and it shows it in the matrix. Is that the section you're talking about?
I think so, yeah. So it has equations 1, 2, and 3, and then towards the bottom it says just equations 1 and 2 that they use. And like equation 1 is f of a minus 100 times 0.4 alpha is equal to negative 50, and then equation 2 is negative 0.4 fa. And I think that's the part where I was like, why is fa negative?
Okay, so I think that's equation 3,
Okay, I've
but
written it wrong.
no worries, no worries. So for equation 3, they have FA as negative because it comes from equation 3. So it's a moment, and they're doing moment about G, which is the center, and the moment G. Here, I can draw it to make it a little more clear. So they're saying this is your wheel, and FA is going like this, and here's G, and they're saying clockwise around G. So when you do your equation, this FA force moves against the moment. See, as the because FA is moving to the right, and when the clockwise motion comes around, the moment is going left. So when you do your clockwise sum of the moments about G, you're gonna have minus this distance, which I think is 0.4.
Yeah, yes.
Yeah, so that's going to be minus 0.4 FA. So that's why that's negative, because this is moving to the right and they're doing a clockwise moment about the center.
Okay. Okay, I think I like tried to do the right hand rule and I probably did it wrong because yeah.
See, yeah, a lot of people, well, not a lot of people, but they really, really preach the right hand rule in engineering mechanics. And I personally don't like the right hand rule. I think that it's confusing and like doesn't like I just think it's confusing, and I just like to think about it visually like this, that the moment is going this way and our force is going against that, so that would be negative.
Okay, thank you.
No problem. So I know I asked already, but was there any kind of problem you wanted to go over? You said practice problems, but
Yeah, I would like to go over more. I know we just did a bunch of them, but impulse momentum.
impulse momentum?
I don't find it
Sure.
because I get the work stuff. Like that's not too bad.
Okay, cool. So let's go back to the review. Oh, okay, this kind of problem. So we already went over number 11, but I can go over number 10 as well. And I think we talked about number 10 in class on whatever day class was on. Friday, question mark? I don't know. Yes, this will be problem 10 in the dynamics review. And in this problem, we have a block with 7 pounds acting on it here at a 30-degree angle. Block is labeled B. And there's a cable going to the inner radius of a circle here that has an outer radius with fixed point A. The inner radius is going to be 3 feet. The outer radius is 4.5 feet. It's going to have a moment acting on it, but C is 28 foot-pounds. We are given the weight of the block as 112.7 pounds. We know that mu sub S is 0.15 and mu sub K is 0.05. We also know that the weight of the wheel is 96.6 pounds. And IG of the wheel is equal to 18 slug feet squared. We're given quite a lot. And says the system is initially at rest. The system is acted upon by an applied couple and an applied force. The couple and the force. Assuming the rope connecting block B to wheel A remains taut, which means that it's not going to go slack at any point. What is the velocity of block B after 2 seconds? So we're looking for VB after 2 seconds. So the way you go about doing this is we have our block diagram. Excuse me, got the hiccups, I guess. We have our block diagram initially at rest. So the first portion is 0. That's going to be plus from 0 to 2, 0 seconds to 2 seconds, starting at rest. That is really small, so I'm going to zoom in. We have the 7 pounds. The weight of the block as 112.7 pounds. The normal force. We have friction. And we have T. This is all dt. And that's going to be equal to the block with its mass times velocity. So if we're solving for the velocity, we can get a couple equations from this. We can start off by saying sum of the forces in the y direction is equal to minus, well, we're going to have integral from 0 to 2 of minus 112.7 minus 7 pounds times, if this is 30 degrees, our y component is going to be sine of 30 to give us our opposite. Plus n. dt is equal to 0. So what this is for is it allows us to solve for n. So from there, we can say that n is equal to 116.2 pounds going up. We need n because we need F. So we can say sum of the forces in the x direction now is going to be equal to 0 plus the integral from 0 to 2 of t minus f plus 7 times cosine 30 degrees. dt equal to mass times velocity. Where here we can replace the mass with the mass of the block because we know the weight of the block, so we can divide this by 9.81 to get the mass. So mass of the block comes out to be 3.5. Wait, what? How was that 3.5? Did I write the weight down incorrectly? Where are they getting this mass value from? It's because I divided by 9.81 and not 32.2. Don't make that mistake on your final. So this is, we're dividing by 32.2 because it's pounds. So that's how we get a mass of 3.5 slugs. And then we can come back and plug in for the friction. Since we know that this is initially at rest, we can say friction of B is equal to it's initially at rest, but the whole system is moving. So since it's moving from 0 to 2 seconds, we know that it's moving because we have a time where it says that it's moving. We use the kinetic friction constant. So it'll be 0.05 times the normal force, which we found as 116.2. So friction there is going to be equal to, well, they don't say what it is, they just plug it in as this. So we can plug in our mass, we can plug in this value for friction, and then T is our only unknown left. So from this equation, we can say that T, well, not our only unknown because we have VB. T comes out to be equal to, however they write it. Yeah, this is how they write it. Sorry. We can say 2T, and this is just this equation being solved. They say 2T plus 0.5, and that just comes from these being added together and the solving through the integral is equal to 3.5 times, and they replace VB with 3 omega. And they say 3 omega because you can treat this as a Arafa stick with a radius of 3 and an omega moving clockwise around the center. So here we have our first equation, and they rewrite it to be 2T minus 10.5 omega A equal to minus 0.5. So that's our first equation there. So the process so far has been setting up these diagrams when they say that we're looking for speed after a given amount of time. So we have starting at rest, integral from 0 seconds to 2 seconds, free body diagram, kinetic diagram, or kinematic diagram, or whichever one it is.
I'm confused with like the integral. Like I understand where the integral comes from, but it's like when you solve for n, you're not doing anything with your integral.
Well, I'm not writing out the steps of solving the integral.
Yeah, but like even if you do that, you're just like you don't do anything with the integral to get that answer. You just do negative. You do the negative 112.7 minus 7 cosine 30. You put those together, move it to the other side, and you get your answer, but you don't do anything with your integral.
That's because these values are doubled and this value is doubled, and it's equal to 0, so the 2's all cancel out.
Oh, you doubled those?
Yeah. So it's from 0 to 2. So you're doing 2 times this times 2, 2 times this, 2 times this, 2 times this, minus 0 times this, 0 times that, 0 times that. Yeah, so then you have your, if these two are doubled and this is also doubled, but then you move these over and divide by 2, it makes sense that it works out.
You just ignore it. Okay. I was confused right
Yeah, that's not true, however, if this is not 0. If this is not 0, you can't just solve the inside of it and be okay with it, because it's not going to work out that way.
And the reason why that is 0 is because that's in the middle of and B is in the middle of the block.
Yes. Well, it's 0 because this is sum of the forces in Y.
Yeah.
And this
okay,
is
okay, that makes sense.
yeah.
I was thinking of moment.
Right. If it was a moment and we were doing moment about here, then yes, that would be. Yeah, exactly. So yeah, that's why it's just this centerpiece. It seems a little weird, but so we got our first equation, and then we can do the same kind of process with our wheel, where we start off with the wheel being 0. From 0 to 2, we have the wheel with the applied 28. The weight of the wheel as, I'm gonna not write that there. The weight of the wheel as 96.6. And we have tension. And we're also going to have an AX and an AY. And that is going to be dt equal to IG omega A. And that's it, because this is stationary, so it's just going to turn. It's not going to move in either direction. So here we can do some of the moments about the center, which we'll refer to as G. And that's going to be equal to 0 plus the integral from 0 to 2 of AX and AY get crossed off. The weight gets crossed off, so we're just going to have T and 28. So that's going to be 28 minus T times the 3 feet distance from here to where the where the cable connects. T is negative because it's moving to the left, and we're assuming a clockwise moment. That's going to be dt equal to IG omega A. We know what IG is. I didn't write the number down. This is 18. I just wrote slug feet squared. So all we're doing here is saying equal to 18 omega A, because IG is 18 slug feet squared. Omega A is unknown. That's what we're looking for here. T is our other unknown. We can do the integral out, and it comes out to be minus 6t plus 56 equal to 18 omega A. So we can rewrite this as minus 6t minus 18 omega A is equal to minus 56. You would set these into your into your matrix for the calculator, and you would get t is equal to, I'm going to write it down there. You would get t is equal to 5.85 pounds. Omega A is equal to 1.16 radians per second. And the problem was asking for a speed of the block. So V is going to be omega R, R being the distance from A to here, because velocity of the block is going to be the same as velocity of this point, the end of the raffle stick. So that's going to be 1.16 times 3 feet, which gives us 3.48 feet per second. So the idea here is that we set up the block diagram and the wheel diagram from integrals from 0 to 2, because that's our time constraint, with all the applied forces and then the expected motion with translation to the right and the rotation clockwise. You can solve for them and replace anything you know, like we established that V is equal to omega, because otherwise we would have VB and omega, and then we have 2 equations and 3 unknowns, and we can't get anywhere. But these equations, and recognizing that the velocity of the block is equal to the velocity at the end of a raffle stick from the center of this wheel. Those kinds of relations are going to be what allows you to use these equations to substitute variables and make the connections you need to establish 2 equations and 2 unknowns, or 3 equations and 3 unknowns, so forth, in the various problems. From there, you solve for what you had, and then you go back to the question, oh, we were looking for velocity of B. What relation did we make with B? We made this relation. Plug in what we know, and we get our answer. So that's the concepts of impulse momentum. Any questions on that?
So those 3 equations are like,
This is like everything for dynamics.
so so it's like the A of the natural force and it's A of the tension force, or is that
It's A of normal force and A of tangential.
a tangential? Okay.
Yeah, and those are represented on a raffle stick like this. AN
Oh, okay, yeah.
and AT.
How would you know when you use either one? Is it just because, like, if you're trying to look for like angular velocity, you would want to use the AN, or if you're trying to look for the acceleration, you would use the angular acceleration one?
So you know which one to use because we can make the relation that
Oh, I see. So like that
right,
one
you
would
can
use
imagine
AT.
an actual raffle stick here in the
Yeah.
center of the wheel.
So in that one, you would use AT, right?
Yes, exactly. If we were looking for acceleration of the block.
Yeah, because they're going that way.
Mhm.
Okay, that makes sense.
Yes,
But it's helpful if you draw the raffle stick.
it's very helpful if you draw the raffle stick. Yes, draw it when in doubt. Draw it, and it will very likely become way more clear.
Sure.
Any question from Zoom on this problem? Alrighty. Do you want to go over anything else?
Can we go over like not easy, but like a force acceleration problems?
Sure. So let's find one. Okay, so this will be problem 13 from the dynamics review. Where we have a wheel with an inner and outer radius on a plane with the inner radius resting on the surface and the outer radius being connected to a cable represented by F with a force pulling down on it. The outer radius is 300 millimeters and the inner radius is 150 millimeters. The mass of the wheel is 100 kilograms. Radius of gyration is 200 millimeters. The center is referred to as G. A vertical force of F equals 200 newtons. Mu sub S is 0.3, mu sub K is 0.25. If you assume a no-slip wheel, you must verify your assumption. So we are asked to find, what are we asked to find? Determine the acceleration of G and the angular acceleration of the spool. Okay, so we are asked to find AG and alpha of the wheel. So what we can do right away is classify the motion. It's just the wheel, so we're just doing one diagram. It's GPM. And the properties of the wheel, it's going to have a mass of 100 kilograms and therefore a weight of 981 newtons. Its IG value is mass times K squared, so 100 kilograms, and we'll use the 0.2 meters. So that comes out to be 4 kilogram meter squared. So we'll go ahead and set up our diagrams. We have our free body diagram with the 200 newtons acting on the left, the normal force and friction acting on the inner radius, and 981 as the weight going straight through the center. And that is going to be equal to our KD diagram, where we have IG alpha and MAG. So what we're looking for here is AG and alpha of the wheel. So we can So they do it by doing some of the forces in X, some of the forces in Y, and then some of the moments about G, the center. What I'm wondering is why we don't just do moment about the point of contact and eliminate all of that and just have one equation.
I mean, why don't you try that? and see if it's the same?
I think I'm going to. So we'll do a counterclockwise moment about the point of contact here, PC. So that's going to be equal to 200 times the distance from, oh wait, it's just this distance. So that would just be the same as the distance from here to here. So it would be 300 millimeters or 0.3 meters. Because this distance is 0.3 meters. Therefore, this distance is also 0.3 meters. Normal force, friction, weight are all going to cross off. So that's going to be equal to IG alpha. IG was 4 times alpha of the wheel. And that would be, we're going from here. So plus mass of the wheel, 100 kilograms, times AG, which can be expressed as a Rafa stick, like this, where AG is equal to AT is equal to alpha R. So that would be an R value of 150 from the center to the point of contact, alpha of the wheel. And there we have one equation with one unknown. So I don't know why they went about doing it with X and Y when you could just do this. So let's see if that comes out to be the same. This should not be 150, this should be 0.15.
Why do you have 100? Or, oh, never mind, never mind.
Yeah, that's just the mass. Let's see. So this is 60, that's 4, and 100 times 0.15 is 15. So that's 19, 60 divided by 19. So that would mean that alpha is 3.16, but that's not what they have. So there must be a reason they do it the way that they do. It's because these alpha values are not the same alpha. That is why. This is alpha of the wheel. And this is alpha of the point of contact. So this alpha is not this alpha. So that's why they do it the way they do it. So we have to go back. So some of the forces in X is going to be minus F equal to minus MAG. That's it for the X, which is just going to get us that F is equal to 100 AG. And that can be written as 15 alpha. Well, they do make it the same alpha value, so why doesn't it work? I'm not sure, maybe I'm assuming something. So that's what they say because they substitute AG like we did, and they say that this is alpha R. So yeah, they say AG equals alpha R, where alpha is unknown and R is going to be, excuse me, this Rafa stick, yeah. Yeah, so they say AG is equal to alpha times 0.15. So that's how they get F equals 15 alpha. And then they do some of the forces in Y. So that's going to be normal force minus 200 minus 981 equal to 0. So normal force is 1,181. And then they do some of the moments counterclockwise about G. So they do take it from the center. So your normal force and weight go away, but we do still have our 200 times 0.3. That's going to be plus because it's moving with the assumed moment. And then we're going to have minus F times 0.15 as the inner radius from center to there. And then that's going to be equal to IG alpha of the wheel. So then they set up the X equation and the mg equation is F minus 15 alpha equals 0. And 0.15 F from there. F plus 4 alpha, 4 coming from the IG value, is equal to 60, which is this portion. So this is just a rearrangement of this equation. And then they use a matrix and they say that F is 144 newtons. And that alpha comes out to be 9.6 radians per second squared. From that, that was the first thing we were looking for, alpha of the wheel, right here. And then we can say that AG is equal to alpha r, therefore equal to 9.6 times 0.15, this distance. And so that would be 9.6 times 0.15, which comes out to be 1.44 meter per second squared to the left. So then we have to, the last part for this problem would be to validate the no slip assumption. So F max here is going to be mu sub s times n. Because it's initially at rest and nothing has moved. We're not working with a like overtime problem. So F max using mu sub s and the n value that we found as 1181 mu sub s, F max comes out to be 354 newtons, and the actual friction that we have came out to be 144. So F actual is less than F max, therefore no slip. And the assumption is valid. Questions on this? All right.
What is that?
All right. Good luck on your exam, man. Does anyone in the Zoom have any questions? All right, well, if you're good, then you're the only one here. I guess I'll go ahead and call it. Good luck with your exam, everybody. Yeah, do your best.